In this video, the following topics will be covered: improving the efficiency of a priori algorithm, cache-based technique, frequent pattern growth algorithm, mining frequent item sets using vertical data format, mining closed frequent item sets. Improving the efficiency of a priori algorithm. Transaction reduction. A transaction that does not contain any frequent k item sets cannot contain frequent k plus 1 item sets. Many variations of the a priori algorithm have been proposed that focus on improving the efficiency of the original algorithm. Partitioning technique can be used that requires just two database scans to mine the frequent item set. In phase 1, the algorithm subdivides the transactions of dataset D into n non-overlapping partitions. If the minimum support threshold for a transaction in D is min-sub, then the minimum support count for a partition is min-sub x the number of transactions in that partition. All frequent item sets within the partitions are found. These are referred to as local frequent items. Any item set that is potentially frequent with respect to D must occur as a frequent item set in at least one of the partitions. Therefore, all local frequent item sets are candidate item sets with respect to D. The collection of frequent item sets from all partitions forms the global candidate item. Sampling. Pick a random sample S of the given data set D and then search for the frequent item set in S instead of D. Dynamic item set counting. The database is partitioned into blocks marked by star points. New candidate item sets can be added at any start. Based technique. Hashing item sets into corresponding buckets. Hash-based technique can be used to reduce the size of the k item sets a priori, which determines new candidate item sets only immediately before each complete database scan. The technique uses the count so far as the lower bound of the actual count. If the count so far passes the minimum support, the item set is added into the frequent item set collection and can be used to generate longer candidates. This leads to fewer database scans than with a priori for finding all the frequent item sets. Cases for a priori candidate generate and test method significantly reduces the size of candidate sets, leading to good performance gain. However, it can suffer from two non-trivial costs. It may still need to generate a huge number of candidate sets. Second one, it may need to repeatedly scan the whole databases and check a large set of candidates by pattern matching. Mining frequent item sets without candidate generation. The disadvantages in a priori algorithms are it may lead to generate a huge number of candidate sets. It may need to repeatedly scan the database and check a large set of candidates by pattern matching. Mining frequent item sets without candidate generation. We can start from the node that has a minimum support count, that is I5. We can exclude the node with the maximum support count, that is I2, for preparing the table. The FP tree is constructed associated with the conditional node I3. The FP growth algorithm, which mines frequent item sets using FP tree by pattern fragment growth. Input is dataset D containing all the transactions, min-sub, minimum support count threshold. Output the complete set of frequent patterns. The method, the step number 1, the FP tree is constructed in the following step. 1A, scan the transaction database D once, collect F, the set of frequent item sets and their support counts, sort F in support count descending order as L, the list of frequent items. 1B, create the root of an FP tree and label it as null. For each transaction in D, we'll do the following. Select and sort the frequent items in a transaction according to the order of L. Let the sorted frequent item list in a transaction where P is the first element and P is the remaining list. So call insert tree, which is performed as follows. If T has child n and that is item name, then increment n's count by 1. Then create a new node n, let the count be 1, its parent link be linked to T and its node link and the nodes with the same item name through the node link structure. If P is non-empty, call the insert tree recursively. Step number 2, the epi tree is mined by calling the epi growth, which is implemented as follows. The procedure is given. If tree contains a single path P, then for each combination of the nodes in the path P, generate the pattern beta union alpha with the support count equals sign minimum support count of nodes in beta. Else, for each AI in the header of tree, generate pattern beta equals to AI union alpha with the support count equals to AI support count. The construct beta's conditional pattern base and then beta conditional epi tree. If tree is not equal to 0, then call the epi growth. Epi growth versus a priori algorithm. Epi growth algorithm is faster than a priori algorithm, but a priori algorithm is slower than epi growth. It is an array-based algorithm, but a priori is a tree-based algorithm. Epi growth is it requires only 2 database scan, but in a priori it requires multiple database scan. The fourth one, in epi growth algorithm, it uses a depth first search. In a priori, it uses breadth first search. Epi growth less accurate, a priori is more accurate. Table shown on the screen. The horizontal data format is converted to vertical data format. This table on the screen, the two item sets in vertical data format, I1, I2, I1, I2 appearing in which are the transactions. The transaction IDs are listed under the TID set. Likewise, all the combinations are for two item sets are given and their respective transaction numbers. Three item sets in vertical data format also shown below. 3 I1, I2, I3. These combination, these item sets are listed in T800 and T900 transactions. Likewise, I1, I2, I5. These combinations are listed in T100 and T800 transactions. Frequent item sets. It's a frequent item set that is both closed and its support is greater than or equal to min sub. An item set is closed in a data set if there exists no superset that has the same support count as this original item set. Frequent item set mining may generate a huge number of frequent item set when the min sub threshold is set low or when there exist long patterns in the data set. How can we mine closed frequent item set? First, mine the complete set of frequent item sets, then remove every frequent item set that is a proper subset of and carries the same support as an existing frequent item set. Next step is to search for closed frequent item sets directly during the mining process. This requires us to prune the search space as soon as we can identify the case of closed item sets during mining.